Well, good morning, everybody, and welcome to the first of today's webinars from Smart Vision Europe. In the first webinar, we're looking at the first topic we're going to be exploring is correlation analysis using SPSS statistics. If any of you haven't joined these sessions before, you should be aware that we do record them, so you'll be able to listen to a recording of it afterwards. And there's a fair amount of slideware here as we jump back and forth between demonstrations and explaining concepts. So we'll email out a link to you to download the materials after the session is ended. And if you find it particularly useful for colleagues who are unable to attend and you get enough of them together, it may be possible for us to arrange a rerun of this on a private basis. The best thing to do is just to drop us a line, send us an email, something like that, and we'll see if we can do that. With regard to asking questions, all the lines are muted, so we can't hear you. But if you use the chat panel, we'll try and check that as we're going along. There's quite a lot to fit in. We generally tend to follow up with people offline afterwards, and you should feel free to send us an email afterwards. If something occurs to you afterwards, if you had a chance to think about it. We'll take our time to respond to it properly to you. And if you don't know who we are Smart Vision Europe. We're a gold accredited partner to IBM, also a company called Predictive Solutions and Data Robot. And we specialize in statistics, advanced analytics, AI, data science, all that type of stuff. Though we do work with open source technologies like R and Python and Spark, and we're a small organization, but we've all got fairly deep experience in the world of analytics and statistics and machine learning and data science. We've all worked in the advanced and predictive analytics industry for, in my case, over 30 years, working for SPSS and SAS and IBM. That means we've got very deep experience of applying advanced analytics and statistics across many different sectors and in many different applications across those sectors. My name's Charles Quinn. I'm an analytics consultant working for Smart Vision Europe, and I'm joined online today by my colleague Rachel, who'll be making sure that everybody's logged in correctly and just checking the chat panel as we're going along. So our agenda today is to talk about correlations and to talk about different types of correlations and to show you different aspects of correlations, useful tricks and useful ways to view it. And to help you make sense of them, and to show you different techniques and to talk about different types of correlation, and also just to remind you of the limitations of correlation. So we're going to start off talking about why correlation is useful, then we're going to look at how we interpret the results of it. Then we're going to look at, doing some additional things like estimating correlations with bootstrapping and also how to get SPSS to highlight the most important or the strongest correlations for you, show you how correlations are calculated, talk about how you can how you can use correlations with things like rating scales or non-linear data. Before we finish up, just putting a few caveats around the concept of correlation and remind ourselves of the limitations of them. So why are correlations useful? Well, correlation is a term that is generally employed. We employ it in everyday speech to denote things that appear to have some kind of relationship. In analytics, correlations, however, are specific values, they're coefficients, and they're calculated in order to quantify the relationships between variables. And this kind of analysis is powerful because it allows us to detect and to measure the strength of linear associations between a near infinite range of factors. So detect by giving us a significance test, a test of significance, telling us whether or not a correlation actually exists, a linear correlation actually exists, and a measure in the sense of a correlation coefficient, because it gives us a value that tells you, sometimes called an effect size, that tells you how strong that correlation is. And typicals with applications people might use is, how does advertising spend affect visits to a website? Obviously, if you're advertising a lot more. How do sales of a product change when competitor pricing changes? So if competitors drop their pricing, one would expect the product sales to go down. Things like in machines, you tend to look at things like vibration or shocks. Sometimes you have sensors on them talk about whether or not a machine's been dropped or something like that, and component part failure. I've done analysis on things like rainfall and pollution, because rainfall tends to cause fields to discharge things like nitrogen and and fertilizers and things like that into water courses. You can look at educational examples of, the amount of time students spend studying on their examination grade. Obviously, things like exercise and weight loss, and things like government spending and population health outcomes. So loads and loads and loads of different ways in which we might use correlations. Now, not only can we measure a linear relationship with correlation, but we can also use one variable to predict the other. And in fact, one could say that things like linear regression are kind of the next step from correlation. If you're going to teach linear regression, you normally start off explaining what correlations are, and then step into linear regression after that because it's easier to understand. And in fact, we will be doing a session later on regression techniques. And one of the first things I'll have to do in that session, because we can't assume that everybody in that session is going to be in this session, is we need to talk about correlations again because we need to kind of explain it to it. For example, if we know how much we're planning to increase our spend in advertising, then because if we can establish a correlation between advertising and sales, we should be able to use it to predict what the increase in visitors to a website is likely to be, or how many more sales we should make if we're increasing our advertising budget. Now, when it comes to interpreting correlations, here we're talking about correlation coefficients, the actual correlation number. It's really important to understand that it exists on a scale. And amazingly, it exists on a scale that runs from +1 to -1, and you can't get numbers that go outside of that scale. The nature of the correlation calculation means you cannot get a number that exceeds 1, and you can't get a number that's lower than -1. So that means it runs along this really perfect scale. It's a linear scale where the closer it is to either of those extremes, whether it's +1 or -1, and the stronger the linear relationship is, the more perfect it is, and the closer it is to 0, then the more random the relationship it is, and the less linear a relationship there is between the two. So simply thinking in those terms, we can see that, zero point 0.5 minus zero point 0.5 or plus zero point 0.5, they're symmetrical to one another. They're exactly the same strength. It's just that they go in different directions. And a negative correlation would simply be, an example of that would be, as one value increases, the other value perfectly decreases. So it might be something like, I don't know, alcohol consumption and reflex reaction time. If you're talking about something like, the more alcohol you consume, the worse your reflex reaction time is, etc., etc. Or you might say, you know, um, CO2 emissions and I don't know, some sort of effect on growth or something like that, or heat. You might get negative relationships there. So correlation scales always run from +1 to -1. They're perfectly symmetrical. 0 in the middle means no linear relationship, and it's linear. We're talking about linear as a straight line because that's what correlations talk about. And we can show some examples of that. You can actually usually illustrate correlations using things like scatter plots. If we're talking about numeric data, so scale data, these are the scatter plots that I use again and again. It comes from a data set called CARS, which I think is a fairly well-known data set. Each one of the points in the data set represents an individual automobile. And here we can plot the relationship between horsepower and vehicle weight, where it simply says it's a positive relationship. As we can see, it's kind of a straight line positive relationship. So it's kind of closer to that relationship, obviously, than that relationship, and probably a bit closer to that relationship than that relationship. So it's kind of trying to form a straight line here. And it gives us a correlation value of plus 0.859. So it's kind of, it's kind of closer, it's kind of about here. It's quite strong positive correlation. And there's a few exceptions, as you can see. There's a few cars that don't really fit that pattern, where they've got really strong horsepower, but they've got really not much weight attached to them. Maybe there's some sort of sports car or something like that. Whereas this is a weaker relationship. It's much closer to 0. It's not completely random, but saying this is time to accelerate from 0 to 60 against miles per gallon. And here, the relationship is only still a positive relationship, 0.434. And of course, what we're saying is that the longer it takes you to accelerate from 0 to 60, the more miles per gallon, more fuel efficient the car tends to be. So these smaller cars take longer to accelerate from 0 to 60 and to be more fuel efficient. And here we have a negative relationship. This is horsepower against time to accelerate from 0 to 60, as we would expect if you have a lot of horsepower, if you've got a really strong engine, big engine, you can accelerate really quickly, and therefore the time to accelerate goes down. So it's a negative relationship, and it's stronger than this one. It's a stronger negative relationship than this one, but it's weaker than this one. It's a stronger. It's not a stronger relationship as 0.859. Remember that these are perfectly symmetrical. And it doesn't, if we flip these variables around, if we put horsepower in the bottom here and time to accelerate in the top here, all it would mean is that the chart looks a bit different, but the correlation value would not change at all. So the correlation value doesn't mean that one depends on the other. It's not miles per gallon against time to accelerate is not different from time to accelerate against miles per gallon. It's not looking at that. It's not paying attention to one being dependent on the other and one being independent. It's just looking at the pairs of them. Hopefully that's clear. Okay. You will get non-linear relationships. You'll get sort of random relationships like this one, which is miles per gallon against mileage. This is against mileage. The mileage is just a relationship between the age of the car, really. It doesn't have any effect on miles per gallon. So it's very close to zero, as we can see, and that's kind of a random relationship. We would expect that correlation to be probably not very statistically significant. And the other thing to bear in mind is that if you have a curvy linear relationship, like this bendy hook-shaped relationship here, correlation can't see that. It just can't see. It basically tries to put a straight line through it. And you can see here I've created this chart here simply by taking miles per gallon and squaring it. So I've artificially created it. Sometimes people will take the square root of a number to straighten out the relationship, or the log of a number to straighten out the relationship so that the correlation can be interpreted more correctly as a linear relationship based on the log of a value, based on the square root of a value. But suffice to say, these are linear relationships it sees. It cannot see non-linear relationships, even if it gives you a strong correlation, which is reasonably strong correlation here. But that's just based on that straight line. It's not based on a curvy line that's going through that. Okay, a word of warning. This is a famous set of charts called Anscombe's quartet, and it basically says, look, you get exactly the same correlation, even when the relationships look really different. So here we have a correlation here of 0.82 between this variable, x, and this variable here, y. But you can get exactly the same correlation when you look at this bendy relationship here between x and y. And you can also get this relationship even if you have one case that's really extreme. It doesn't fit this pattern at all. If you took that out, you might get a different correlation, probably get a different correlation value. And you can even get it when you only have two values. I mean, here we've got a value here of 8 and probably a value of 20 or 19 here or something like that. It looks like 8 and 20. And it still gives you a correlation of 0.82. So the point is, if you should investigate the relationship, do a chart or something like this, a scatter plot or a bar chart, if it's an ordinal variables, we'll see later on how to do that. So that you can, make sense of the correlation. Don't just take the number, have a look at it and see if it looks more like this rather than like this. Because the correlation is just a calculation based on the values of the variables. It's not looking at charts or anything like that. If you want to run correlations in SPSS, you'll find them under Analyze, Correlate Bivariate. Okay, this is the standard place. Bivariate meaning pairs of variables. And here I've got a data set here where I'm looking at the correlations between three pairs of three variables. Current salary against beginning salary, and beginning salary against education level. So I'm going to get three correlations, aren't I? I'm going to get current salary against beginning salary, current salary against education level, and beginning salary against education level. In fact, as we'll find out, it will actually get 6 correlations because it'll do current salary against beginning salary against current salary, which will be the same correlation, education level against current salary against education level, same correlation, beginning salary against education level, and education level against beginning salary, same correlation. So, and if we run with the default settings in this, what we'll get is a table that looks like this. Quite confusing. Got a lot of numbers in here. Here is the actual correlation. Look, current salary against itself is a correlation of 1. Well, of course it is. And current salary against beginning salary is a correlation of 0.88. Quite a strong correlation here. The double asterisk indicates that it's significant at the zero point zero 0.01 level, meaning it's, whereas a single asterisk would mean it's significant at the zero point zero 0.05 level. The N number here is simply telling me the number of cases. So it's showing me current salary against itself, showing me current salary against beginning salary, and it's also showing me beginning salary against current salary. Look, here's the same numbers. So look, we can highlight these. Look, here's the numbers. Each correlation is repeated twice. It's redundant. We don't really need that, do we? It doesn't make sense, but it makes it look slightly more complicated as a table. So these are the correlation coefficients. The table's a mirror image. The second thing is the diagonal values are all equal to 1 as they are variables correlated against themselves. So this is kind of useless information. You don't need that really, because it's always going to be equal to 1 no matter what it is. And the third value is the significance values, which show how likely one is to get a correlation like that, assuming there's no relationship between the variables. So as we'll find out later on, very important for you to understand, the significance value is not telling you that it's a strong correlation. It's not telling you that that it's a notable correlation. It's simply saying whether or not the correlation probably exists, kind of. That's all it's saying. Even if the correlation's really weak and not very interesting, you can still get a significant result. And we talk about this a lot in our webinars. We talk about when something is statistically significant, but it's not really that significant in real life terms because it's not notable. Okay, what can we do about this? Well, sorry, then the last number here at the end is just simply telling us that there were 474 cases in each pair to make that correlation. You might have a missing value here. You might have a few missing values in the education level, in which case you might not get 474 cases, you might get 472 or 470 or something like that. So the number of cases might not be the same. So it's simply telling you how many cases were used to calculate that correlation. So I'm going to run that. I'm going to jump out to SPSS here and just show you how I did that. I went to Analyze, down to Correlate, to Bivariate, just as I said earlier on. I'm going to pick up beginning salary, current salary, and education level, put them in there, and you'll see exactly the same results that I got earlier on. There you go. Same results I got earlier. But if I go back to correlations and check these little boxes here, look, if I say show only the lower triangle, so don't show me the mirror image, and don't show the diagonal, and I run that again, look, I get a much smaller correlation table here where it's not repeating everything all the time. It's saying I'm not interested in beginning salary correlated against itself, and I'm not interested in the mirror image of it. I just want the three correlation values. So I can do that here. I can go back to Analyze, Correlate, Bivariate, and simply say show only the lower triangle and don't show the diagonal. And I run again. It's the same numbers that we saw beforehand. It's just getting rid of a lot of the dross that we don't need in there. So here's the numbers again. And we should bear in mind that sometimes we've still got three values in each pair. So we've got the significance value, the N number. If you do like a really big table, that can still be quite confusing to look at. So you can actually double click on the table and you can call it what's called the pivoting trays here, pivot controls, and you can put statistics into what's called the layer box. And then you can say, just show me the correlations, look, or just show me the significance, or just show me the number of cases. Yeah, quite useful to be able to kind of help you make sense of that. I'm just going to quickly show you why that's useful. If I do a really big table, I'm going to do a really big table here. I'm going to put in everything else here, age, since I've put all these guys in. Look. See, it's still quite a big correlation table. And I can double click on it and then go to pivoting trays here. I can go to put statistics up in there, and that's it. It's much simpler. It's much easier for me to make sense of, and I can see the strongest correlations and the weakest correlations. In fact, I can even go further than that. I can go to bivariate correlations, and I can go to style. Look, I can go to style here, and I can say, look, just show correlations by default above 0.5. That's pretty strong, and it gives me this like really livid color. I'll make it a bit less livid. Hit continue and click look, and it highlights the strongest correlations. Isn't that useful? Or I could even traffic light it. I could go back in the style and I say, actually, do you know what? I want show me anything above point, I don't know, 7 and show that as say orange. And then add another row to it and say, look for the value correlation And anything between, let's say, between, I don't know, points, I don't want to make, I don't want less than equal to, I'll say higher or lower exclusively. I'll say, yeah, point, need to be careful with this because it's very fussy. I'll say point 0.7 and 0.4, something like that. See if that works, see if it finds any use. And I'll say, again, don't make it too livid for me. Okay, so now it's finding like slightly weaker ones and stronger ones. So you could do this. You could get it to highlight, and I could double click on that again, and I could say, okay, show me the statistics. And look, here's the strong correlations. Current salary against beginning salary, really strong. Age of employee against previous experience in months, of course, because the older you are, the more previous experience you have. And then slightly weaker, current salary against education level and beginning salary against education level, zero point 0.6. And then the rest, the remaining ones are all kind of, they're all less than zero point 0.3, I think. So they're all kind of weaker. Most people would say anything below zero point 0.3 is, pretty weak at that stage. And zero point 0.3 is kind of marginal for, for a correlation, in terms of strength of correlations. Okay. What else can we do? Well, actually, I can go back to this and I can say, um, I'm actually just going to pick out, I'm just going to hit reset here. I'm just going to look at, say, education level against beginning salary. And this is basically, let's just run that. I'm going to say switch off the diagram, click OK. You can see here, look, it's showing me a correlation here of 0.6. So this is a notable correlation. It's saying, the higher your education level is, the higher your beginning salary is. And vice versa. The higher your beginning salary is, then probably the higher your education level is. But this is based on 474 cases. I can actually do something called bootstrapping. Bootstrapping means I can actually ask it to take multiple subsamples of the data and just calculate over 1,000 subsamples. Look at it's doing it. It's just running through over 1,000 subsamples to say how much does that correlation vary between one sample to the next. And it's saying, well, sometimes it's as low as 0.58 and sometimes it's as high as 0.69. So it gives me an idea of where the true correlation value is between beginning salary and education level in the population, if you like, rather than just in the sample. So it's a robust estimator, if you like, where the true calculation value is, and where the true correlation lies within the population. It's a bit like doing 95% confidence intervals, except here it's actually just resampling the data rather than using standard errors, which is what it uses when looking at averages. And in fact, you can see it's based on 474 cases. If I went to data here and went to and said select cases, and I said, okay, look, just select a random sample of cases and just look at 10% of the data, and then reran that procedure as I did earlier on. There it does it bootstrapping again. Because it's only based on 10% of the data, it can't be as reliable now. And now the gap between the lower and upper is much greater, isn't it? Because look, it's 0.328 to 0.72. Because it's not as reliable because it's only based on 36 cases as opposed to 474 cases. So it gives you an indication of how much your correlation value is likely to vary from one sample to the next if you were to repeat the sample again and again based on a similar sample size. So it's really useful in that sense. If I go back to, so I need to switch off this select cases here, go to select cases and say all cases. So now we're back to looking at all cases. And I need to remember to switch off bootstrapping here because it's going to be switched on when I come back to doing any other correlation. So I run that again. We're back to where we were at the start. Okay, so that's kind of a quick tour through what we call our Pearson's correlations. This was a Pearson's correlation that we were running. It's a standard correlation invented by Carl Pearson, probably back in the 1930s, 1940s, something like that. How is it calculated? Well, it was actually calculated by it was formulated to be calculated by hand. And Pearson's correlation is also known as the product moment correlation. And correlations are often described as data moving together. It's kind of not very good description, I think, but that's what it means. As one value increases, the other value increases. Something to bear in mind is that a Pearson's correlation is a parametric procedure. That means it has assumptions about the data. Later on, we're going to look at a non-parametric correlation and talk about the differences between them and how it gets around this. But strictly speaking, Pearson's R assumes that the level of measurement of the variables are continuous or scale, i.e. interval or ratio. And that means that they're real numbers. They're not rating scales. They're not very happy, not so happy, strongly agree, don't agree, you know. They're not rating scales, not Likert scales. They're real numbers. Where 33 means 33, or where, you know, 36.7 indicates, you know, somebody's temperature or something like that. It also assumes that there aren't too many extreme outliers in the correlated variables because we know that affects things. And it kind of assumes the data is normally distributed, but really people don't really worry about that too much. It says if this is, you got a reasonable sample size of, you know, more than 30, 40, 50 records, something like that. It's pretty robust with that assumption. That's Pearson's R. That's our default correlation. And the formula for it is, because we're going to calculate it by hand now, if you actually look at it, it's kind of magical because it's just the ratio of two numbers. What this, the number up, whatever number this comes to, and whatever number this comes to, it's basically the ratio of two numbers. And magically, it always runs, as we know, from -1 to +1. But in fact, if don't get frightened by this formula because it's actually quite simple. The xi here indicates individual scores for one variable. Let's say that's education, and y1 indicates individual scores for another variable. Let's say that's starting salary. And all it's doing is looking at each individual score, each employee's score for their education against the average education for the entire sample for each individual score. And then the same for starting salary, each individual starting salary against the overall average salary. Then it repeats the thing again, but this time it squares the differences. It sums them individually, multiplies them together, and takes the square root of it. Now, you don't have to parse all of that, but the point is you could do this by hand. You could actually calculate this by hand. We actually have got a little example here of this. So I've got a little data set here. Let's see, calculate a correlation here. So I've got two really simple columns here. One is people's scores on the maths test and people's scores on the physics test. And I'm not going to do it. I'm not going to get my calculator out and do this. But if I've got some syntax here that runs this, and I can do the top part of this formula here, this bit here, which is I just say, okay, let's look at these two numbers here. Let's do the difference between individual scores and their mean. And I can run that, and it runs that, and it calculates the difference between the individual score and the mean for the x variable for physics and for maths. So it does that. And then I say create a variable by multiplying these two columns together. So we do that. That is that bit where we multiply these two columns together. This bit here with the two columns. So it's adding that together. And then what we do, there's a big sum sign there. So it says, okay, create two variable. Oh yeah, we're gonna compute the sum. Now, create two variables by squaring the two mean difference columns. We're just working our way through it, and there's a square of the two mean difference columns, and now moving down to the bottom part of it. This is work out the sum of x mean and y mean. So it just does that. It's a bit messy. It's just telling me. I've just done it manually. It says it's 10. That's what the sum is. Okay, fine. So we've done that. This is create a variable with that value. Okay, well, fine. We'll just do a variable. It's not like Excel where you can put the whole formula in at the top here. You're going to calculate them. There's that value. We stick that number in, number 10 as a constant. This is work out the sums of these two guys. A squared x mean x and squared y mean y. Run that. And that works out the sum of that. And then create two variables, sum of that. Okay, that's done that. And then basically get to the end. It says use these last three columns to compute your correlation coefficient. And we basically run that. And we get this number at the end here, which is 0.648. That's our R value. Well, do we know if that's true? Well, let's run it. We'll go to down to correlate, bivariate. There's physics and math. These are two original variables here. Run that. What's comes out is 0.648. So you could do it by hand, and it was designed to be done by hand. I guess I'm just doing that to try to demystify it a wee bit for you and show you that, yeah, it's a bit involved, but I mean, in terms of all the different elements to to the equation. There's not very many elements to it. It's just averages and individual scores and like summing them and multiplying them together and taking the square root of them, then the ratio of one value to the next. It's really quite simple in terms of the concept behind it. But it's amazing because it comes up with this number that runs between -1 and +1. Okay, so far we've been looking at variables which are numeric in nature. They're numbers, It's like, people's years of education against their salary or their age against their salary or something like that. You know. So that's all very interesting. But what we're not looking at is things like, customer satisfaction against, I don't know, against people's salaries or, what likelihood to recommend against, frequency of visit or something like that. I mean, you visit on a sliding scale, you visit like more than once a week or less than once a week or only once a month or, less than once a year or something like that. These rating scales that you get. So these are called rank order variables or ordinal variables. And how do we calculate correlations? Well, it turns out that you notice in the correlation dialogue here that Pearson is the default that's switched on, but there are these two other correlation coefficients. One's called Kendall's tau b, and one's called Spearman's. And rank order or ordinal variables refer to variables such as rating scales. These are not true numbers. We tend to think of rating scales as true numbers because we ask them to score from 1 to 7, but they're not real numbers. The difference between being very satisfied and slightly satisfied, sorry, the difference between being very satisfied and satisfied is not the same as the difference between being slightly satisfied and satisfied. Just because you put a number on it doesn't make it a real number. It doesn't mean three. Three doesn't mean three things. It just means first, second, third kind of thing. And those are numerals. And two techniques exist in the SPSS that deal with these kind of data. Spearman's rho, Spearman's, and Kendall's tau b. Both are non-parametric methods. They do not make assumptions about the data. They don't assume normality. They don't assume the data's continuous or anything like that. So Spearman's rho is the simpler one, and it works by ranking the original values from the lowest number to the highest number. And for this reason, sometimes referred to as Spearman's rank correlation. You'll hear it described as something that detects a monotonic relationship. A monotonic relationship is just one where, as the size of one variable increases, the values of the other variables also increase, or vice versa, where the size of one variable increases, the other variable decreases. So it doesn't mean that they increase by the same degree or anything like that. It just means that there's a general direction to it. Spearman's correlations are not affected by outliers, and we'll see why that is the case. But analysts should still consider whether extreme outliers are valid reflections of the population under consideration. Now look at this relationship here. This is a relationship. It's obviously a non-linear relationship. I made it bendy, and I've created it. It's like the number of calories you consumed by your restaurant bill. So, I've got a little data set here called Fancy Restaurant I've created. And here we have it. Fancy Restaurant. Here's this chart. I can just recreate this chart. I can go to graphs up here and call up scatter plots. So I'll go to restaurant bill. Let's see if I put scatter plot. There we go. I'll put calories up the side here and restaurant bill along the bottom here. Click OK. It's a bendy relationship that we saw in the chart. Okay, so non-linear relationship. Spearman's rho, you could use Spearman's with this, even though it's not ordinal variables, not rank scales. But Spearman's will get around this, and one of the ways in which Spearman's works is because it doesn't look at the individual values; it ranks them. So, so let's have a look at that. How does Spearman's work? Well, first of all, let's just put a straight line through it. I mean, I could literally go to this chart here and just kind of force SPSS to put a straight line through it, and that's effectively what the correlation's doing. It's putting a straight line through it, trying to put like a regression line through it, actually. Yeah, it's this one up here, really. It's not that one. It's really a kind of regression. I'm trying to put a straight line through it, and you know, it's ignoring the bendy relationship. So you'll still get a correlation out of that. So I go to bivariate correlations here and say, yeah, just give me the standard correlation. Show only the lower triangle, don't show the diagonal. It says, oh, look, comes out as 0.864. Okay. Whereas if I said, what's the Spearman's correlation of that? Amazingly, Spearman's rho comes out as one, means it's perfect. You think, well, how can it be perfect? Well, that's because if we rank the data, they do perfectly match it, and Spearman's rule only looks at the ranks. You can actually ask SPSS to rank data for you by going down here to rank cases, and you can put in restaurant bill and calories consumed. Click OK at that point, and look, the lowest restaurant bill has the lowest calories. And the highest restaurant bill has the highest calories because they've got like a tasting menu or something like that. They're eating lobster or something like that. So one corresponds perfectly to one, two corresponds perfectly to two, and three corresponds perfectly to three. So that's why it's giving you a correlation of exactly one, because it's looking at the ranks rather than the individual values themselves. So if I mess these up a little bit, if I just change some of these values and said, actually, you know what, I'm going to make that 2000. I'll change that to just 412. I'll just mess them around a little bit here. I'll make this 985. I'll make that 3115. I'll make this, 1500 or whatever. Just play around with it a little bit. I'll make that like a 100. I'm just playing around with it. What happens now when I do, the ranks aren't going to be exactly the same. They're going to be different from one another because they're not going to look 15 and 8 doesn't match up as well. So that means that when I do my bivariate correlation asking for Spearman's. Click OK. Now the correlation value is lower. It's not 1 anymore because it's not perfectly correlated with each other. So this is useful if we're going to be looking at ordinal variables because it just basically ignores them, doesn't treat them as numbers to begin with. It treats them, it kind of makes them ordinal to begin with. It just turns them into ranks, which is what an ordinal variable is. Anyway, so that's really useful. Now there is an alternative to Spearman's. It's called Kendall's tau b. And Kendall's tau is regarded as a wee bit more robust. Some people think of Spearman's as a bit basic, kind of quite simplistic, and it is quite simplistic because it's just taking the ranks. Kendall's tau b works by ranking the original values from the lowest number to the highest, but this time the analysis focuses on what's called the degree of concordance and discordance between the two ranked columns of data. That means kind of the degree of agreement. And it also means that Kendall's tau b is very, very process intensive. If you've got a big data set, you may find it takes a very long time to complete or calculate even with a decent PC. It can take a while for it to calculate it. If it ever calculates it, if it's big enough, I find sometimes I've just had to leave it and give up on it. But it is regarded as a bit more robust. So here we have a little data set here where we're looking at things like movie title. So we've got these 10 different movies. And I just looked at their IMDb rank and the Rotten Tomatoes rank relative to each other, which one came out. And what Kendall's tau b is, it's kind of looking at where the ranks are relative to each other, how big a difference there is between how much disagreement there is between, how IMDb ranks the movie and how Rotten Tomatoes ranks the movie. So it's kind of interesting in that sense, which one, where the differences are in terms of their ranks. So if I did, some argue that the significance estimates and confidence with Kendall's tau b tend to be more reliable than Spearman's. Kendall's tau b tends to give smaller correlation values than Spearman's and can also take longer to calculate. So let's compare one against the other. I've got a little data set here. I'm going to just show you this little data set here. So I'm going to say, little data set here, it's called Kendall's comparison. And it's actually just based on these, I've got two or three different rating scales here. This is from a data set that looked at attitudes in America, sort of social attitudes. And a lot of it was focused around sort of economic pressure. So if I just right click on this and show you what this table is, it says asking people how much they agree with the following statement. No matter how fast our income goes up, we never seem to get ahead. 13% of people definitely disagreed with that. 23% of people definitely agreed with it. And then we have another variable here, and it's different. It says, our family income is high enough to satisfy nearly all our important desires. 13% definitely disagree with that. 18% definitely agree with it. Okay. So this is a rating scale. It's going to definitely agree to definitely disagree. And there are obviously well, one would be, you'd expect one to be negatively correlated with the other, because the agreement with this is, yeah, we're really struggling. And the agreement with this one, the higher the agreement with this one is no, we're doing all right. So if I did a bivariate correlation here and I looked at these two variables here, one against the other. Now, if I just did Pearson's to begin with, did Pearson's to begin with, correlation is minus zero point 0.4, so it's a negative correlation, okay? What happens if I do Kendall's tau B? Sorry, what happens if I do Spearman's? Spearman's is a rank order correlation. It's a little, just a teeny bit lower at minus 0.113. Some people would say that's more appropriate than using Pearson's because this is rank order data, not true scale data. And if we did the next one, we said, okay, let's do Kendall's tau B. Let's see, does it calculated pretty quickly there, but it's actually even the correlation coefficient is even more conservative at minus 0.34. So bear that in mind that Kendall's tau B is a good alternative if you're trying to be very conservative, and you're looking at rank order data or non-linear data because data that's just not linearly related. Then that's a good alternative, a good way to go about doing, assuming that the data set isn't so big that it's going to take a really long time to calculate. Now, what happens if we wanted to actually represent the relationship between these two variables? You saw earlier on I was doing scatter plots. Well, scatter plots won't work in this case. If I try and do a scatter plot, a lot of people do this and they say, oh, what's wrong with my chart? It's because they're not thinking clearly about what it is a scatter plot tries to do. These are not these values here are just rank order values. They don't. If I just show you the values, like they're just ones and twos and four. Yeah, there's no decimals here. So some of these always going to score one here and score five here. Some of these always going to score five here and score one here. Just is. There's bound to be some case there. So if you're doing do a scatter plot that, you're going to find at least one case where one's five. Every possible combination is probably available in these. What we've got 8,000 values here. So that means I'm going to get a very strange scatter plot when I try and do a scatter plot of this. If I do this and say, okay, let's look at family income along the bottom here, and I'll put no matter how fast our income's going on the top here. Look at this. Click at this. You get this type of scatter plot coming out. Because there's at least one person who definitely agrees with this statement and definitely disagrees with this statement. And one person who definitely disagrees with this statement and definitely disagrees with this statement as well. Now, for all we know, there's only one person there, but there might be 5,000 under this point. We just can't see them all. And there's a thing called jittering where it kind of shakes the dots so you can see them a little bit. It's not a great way to represent the relationship between two ordinal fields, though, using scatter plots. It's just not a good way to do it. So how might we get around it? Well, what we would do is we would normally do something like a stacked bar chart. That'd be an easier way to do it. So I could do this. I could say, I'm going to change this to a stacked bar chart and put that in there, say. And then I could say, okay, this family income, I'm going to color that by no matter how fast our income's growing. Now, the colors are a bit weird and it doesn't stack to 100%. So I'm going to have to change that. So there are different ways in which I can do that. But if I want to change it to 100%, I can go down here to percentage. That's one way in which I can do it and say total over total over each X category. And it should work that way. In terms of chart appearance, well, I got different templates I can use. Okay, I've got these. Change it. But we actually allow people to download chart templates from us. We've got ones user specified. We created our own chart templates, and this is one of the ones I use for these types of charts are called Lollipop. And you can see that they're colored in order, so red through the green, yeah, like a lollipop. If we click OK at that point, you can see that red indicates definitely disagree and green indicates definitely agree. And as you can see, there's this negative relationship here as definitely disagree here tends to have not as much definitely disagree in this group, but definitely agree here tends to have a lot more definitely disagree in this group because they're negative relationship. And that's a much easier way to see the correlation because these are, after all, categories. These are category fields, they're ordinal categories, they're rank order categories. So that's quite important, we need to understand that, certain types of data has certain types of data needs to be treated appropriately for the correlation that we're trying to trying to answer here. We're trying to investigate here. Um, I am trying to see the questions. I'm pressing escape, but of course the meeting controls aren't appearing. If you could see them for
Yeah,
me,
let me read them out for you.
yeah, because I
Yeah.
can't see them. It's not
I've
coming
got
up.
how can we correlate non-linear relations?
There you go. Well, that's right away. Non-linear relationships are correlated using Kendall's type B or Pearson's correlation.
I've
Or alternatively, you can linearize the data sometimes by taking logs of the data or square roots of the data. You saw on my earlier scatter plot there that I had artificially created a non-linear relationship. You saw this one here. I artificially created this non-linear relationship by taking the square of one. I took miles per gallon. I squared it to create this bendy non-linear relationship. So if I took the square root of that, that would straighten that relationship. That's another way to do it. Yeah. So that's one.
okay. How do you do it for non-parametric data?
Well, non-parametric data is what we've just done there already. So non-parametric, we wouldn't call it non-parametric data, but data that's appropriate for non-parametric tests would be Spearman's and Kendall's. Same answer. Yeah.
Yeah. And then the others are more about some other follow-up sessions that I will run.
Okay, that's fine. All right. Okay, that's fine. Okay, let's talk about it because people often, you always hear politicians saying correlation's not causation. It really gets up my nose, but it's one of these things that people say all the time. They say correlation's not causation. Okay, yeah, you're right. You're right. Correlation does not indicate causation, but then you're not saying that for correlation, okay? And significance does not indicate notable. So let's look at significance does not indicate notable first of all. I did talk about this, but if I went back and just looked at this data set that we had earlier, this employee data set. Let's just look at this one, okay? Let's do some bivariate statistics here. Let's pick these up, and I'm using just continuous data, and I'm saying I'm on Pearson's here, and I'm saying show only the lower triangle, don't show the diagonal, click OK, just to kind of have it that. Let's just look at this in a wee bit more detail. Let's see if we can find a weak correlation which is significant. Okay, look, here's age of employee against current salary. Look, the correlation here, I think you'll agree, a correlation of minus 0.145 is not a very notable correlation, is it? Not notable. It's a really weak correlation. It's very close to random. But look, it is statistically significant. The two things are not the same. So any reasonably strong correlation will come out statistically significant. Significant does not mean, and never did mean, notable. Okay? The significance test is not testing whether or not it's a strong correlation. It's testing whether or not the correlation is likely to be zero in the population. And it's saying, no, it's not likely to be zero. Not with 474 records. But that doesn't mean it's a strong correlation. So that's a first thing to get your head around is that, that's a limit. It's not a limitation of correlations. It's a limitation of correlation coefficients, significance values. They're not the same things. A significance value is not an effect size. An effect size is saying, yeah, okay, this is how strong something is. A significance value is simply saying, yeah, it might be zero or there might be no difference. It's not saying it's a big difference. So they're two different things. That's the first thing. Second thing is this business of causation and correlation. Yeah, you're right. Okay, so there's no relationship between there's no a causal relationship probably doesn't exist between ice cream sales and sunburn. You know, eating ice cream does not burn your skin. Okay, doesn't cause one, but there is a relationship, isn't there? So if anyone ever says to you, "Well, correlation is not the same as causation," you say, "Yeah, but it does indicate that there's likely a relationship between the two factors." And there is a relationship between ice cream sales and sunburn because people tend to eat ice cream in situations where they're more likely to get sunburned, i.e., when the weather is hot. So that's the first thing. The second thing is if you really want to be smart about it, you can just retort to them and say, well, actually correlation doesn't imply causation necessarily. Correlation doesn't imply causation, but causation doesn't necessarily imply correlation. You can have things which one thing causes another, and it doesn't appear to correlate, because there are other factors involved or it's a more complex relationship. So, stick that in your pipe and smoke it. And the other thing is that you do get these charts. A lot of people that go, oh, look at that. They tend to be trend charts. They tend to be trends. You'll notice that they always tend to be time trend charts. Where number of people who died becoming entangled in their bed sheets and per capita cheese consumption. It looks like there's a correlation there, but it's a trend chart. So it's very easy to get a trend that looks similar over time. Now, we know that they can't accurately measure curvilinear relationships because we talked about that. If you get a curvilinear relationship, you need to investigate the correlations here. This is amps against volts here for machines, you know. So you might, for example, say, okay, well, I'm going to look at the correlation across a certain range of values, say above 13 and below 14.6, something like that, and say that's where my correlation is focusing. Outside of that, they're extremes, you know, so that make a difference. If you're looking at things like, you know, people's wealth or something like that, and you've got billionaires in there, yeah, it's probably going to affect things. Further mind, they are influenced by the range of values in the sample. So, for example, you could actually take a sample and split it into two groups. You can say, what's the correlation between education level in years and beginning salary? Well, for those who earn up to 30,000, the correlation is 0.6. But after 30,000, there isn't much of a correlation. Look. So you need to bear in mind that, you know, over certain groups, different maybe different populations within your sample, or your samples actually referring to different groups. And the other thing, of course, is that, you know, they can be unduly affected by extreme outlier values. So if you put in an outlier value here, look, this is 0.731, good correlation here between beginning salary and current salary. I add in somebody who's an outlier, and that affects the correlation. Now, if that's obviously going to have a greater effect if the correlation is if you don't have very many observations. The more observations you have, the less likely an individual extreme value is going to affect it, of course. Okay. The last thing I just want to point out here is just a really useful thing I find that probably I don't mention enough is that there's a little procedure in SPSS people don't really use very often called split file. And it's kind of a misnomer because it doesn't really split the file, it splits the output. But if I look at, say, again, the relationship between salary and, let's say, education, let's say beginning salary and education, and we're going to reset here. I'll just say, okay, show lower triangle, and I'll look at education level in years against beginning salary. There we go. I click OK. That's for all 474 cases there. If I go to data and split file, not split into files, but split file, I usually go for this third option, organize output by group. And when I say split that by employment category, there are 3 employment categories. There are clerical workers, custodial, and managers. And click OK at that point. What that will do is it will split all my analysis by those 3 groups. So if I rerun my bivariate correlation at that point, you can see I get 3 tables, one for the clerical, one for the custodial, one for the managers. And look, for the clerical workers, the correlation is 0.516 now. For the custodial workers, it's actually negative, saying the higher your education level, the lower your beginning salary. There's only 27 people in there. And for the managers, it's actually 0.4. The correlation is actually weaker individual when we look at them individually. But what it's doing is it's a good way to find exceptions to the rule, and don't assume that the same correlation exists across all the different groups. And this simple procedure here, we're using split file, data split file, allows you to split up the data. And it's a good little trick to apply. Okay. Just so you should be aware, for our customers, they get free access to our online training materials. But our non-customers, they're available for purchase. You can download them. And we can help with processing and analyzing your data, of course. We have self-paced and in-person training courses in how to use SPSS and the appropriate statistical techniques. And we offer a mix of consultancy and training, whereby we do the initial work and then teach you how to replicate it. You can source your software directly from us, often with discounts. And we can help with selection, piloting, and implementation of analytical tools. You can buy your SPSS software directly from us. As I say, we offer training consultancy. We even offer identification and recruitment of analytical skills into your organization. We generally offer no strings attached advice to all comers, irrespective of whether or not the customers. And we have formal technical support services. If you have your software sourced from IBM, you can actually switch your license to us, and we'll and we're a smaller company. We're experts in SPSS, of course, and we can provide the technical support services directly around that. Hope you find that useful. Later on, we're going to be looking at decision trees, another topic where we're looking at relationships between variables, multivariate relationships between variables. If you've never looked at decision trees, I would recommend it. I think it's really useful. And then we're going to look at kind of an extension of correlation. We're going to look at linear regression, which is very much the sort of bigger brother to correlation. In the meantime, I hope you found that useful, and we look forward to you logging in again.